All right, so let's go over this. So first of all, general comments. The grades were really good. The answers I saw on tests were really good. By and large, I was really happy with where people were. This is the best that a class has ever done on the midterm exam. And this was not an easy midterm, okay? It actually was on par with the difficulty of what I've given in the past. But lots of A's and B's and some C's and some D's. But the average was something like 81% or something like that, which is just crazy high. So that's really good. No, don't drop the class. There's usually a bit of a curve anyway, but usually people do better as the course progresses. Because once you understand linked lists, for example, really well, then trees become a whole lot easier. Even though it's a more complex data structure, going from a linked list to a tree is a lot easier than going from, 224 to linked lists, right? And going from trees and linked lists to balanced trees, right, is an even smaller step. So these things usually build, which is good. So I think by and large people are in good shape for this course, which is excellent because this is the lead into 223, right? In 223 we'll be using data structures, but we'll be learning Java, so different language, different paradigm, it's object-oriented, but your knowledge of data structures from here will let you walk right into doing things with some of the classes that we have in Java, and then you can start having fun with writing programs, and we'll write programs that actually do things instead of just type in numbers and they go into a list or a queue or whatever. So we're moving towards 223, which is good, and then of course that prepares you for wherever you're going after Clark, and you should be in good shape. All right, so let's go through this and see what we got. So consider a structure named data, which will be used to hold the following items. So there's a character pointer named level without a predefined length, so you can't just define it with bracket, 10 or something. A single character named xc, an integer named val, and an array of 10 integers named stuff. So question 1 was to make a struct statement to define this structure named data containing the above fields. So something like struct data. And then you just spell out each of these variables as a piece of the structure. So a string is a char star level, a character xc, an integer val, and then an array of 10 integers named stuff would be integer stuff 10, and close bracket, semicolon. So level has to be a pointer to a character, right? Because it's a string, it's an array of characters, null terminated. So we don't know what the length is, so it's just a pointer to a character. But xc is a single character, so that's just defined as a char, not a char star. Array of integers means this has to be an int. A lot of people did char there, I think just because we're used to doing arrays of characters for strings. And you cannot do the following. Some people tried to do this. That will generally give you a compile error. Okay? I don't think there's ever a reason you need to use this kind of notation. You can usually get away with saying character star level, right? If you really mean an array of an undefined length, then go ahead and do that as an argument to a function. That's okay. But inside a structure, the compiler will complain about this. It turns out if you put this at the very end of your structure, it'll let you get away with it. But it freaks the compiler out in trying to figure out how much space you need for this because it doesn't like this undefined array. But you can always do an array like this, right? So that's a better way to stick with in general. All right, part B was to make a statement declaring a variable named code of type struct data star, and that's pretty straightforward. Struct data star code. Right, that says code is a pointer to a struct data. Part C wanted to use a malloc statement to set code to point to a block of memory large enough to contain a struct data. So that's just code equals malloc size of, and then the thing that you're going to put in there, a struct data. And you don't want star code, right? Because that doesn't really mean anything. You can't assign something to, well, that would presumably take the thing code's already pointing to and change it to be equal to this. But when we say this, you can imagine that code is null. It may not actually be null, but it may be, right? So we never want to use the thing pointed to by code after a declaration like this until we set code equal to something. So code equals malloc does exactly what you want. It makes code point to an actual location in memory. And then part D, we wanted to initialize. So you wanted to set level to x17. So if this is code, code level equals x17 will totally work. If you try to string copy, first of all, string copy, first argument is the destination, second argument is the source. So you could try to do this. And that would work, except that you're going to get a seg fault. Because inside here, we've said level is a pointer to a character. But what you should be thinking is, at this point, level is probably null. It's not pointing to any particular location. It's uninitialized. And so if we try to do this, it's saying copy these characters into memory starting at location 0. And that's going to seg fault. If you wanted to do this, first you would have to do something like code arrow level equals malloc. And you'd have to set up 4 bytes in memory. And now level is pointing to a chunk of memory that holds 4 bytes. And now you can string copy x17 and a null terminator into that location. But you don't need to do any of this. Right, this will work just fine. The compiler will create a block of memory. It will initialize it to x17 followed by a null, and this will set code arrow level to whatever that address is. So it basically does these things, but it does it at compile time.
Is this okay if it's written in a function? Will that
If what's written in a function?
all this code, if you set code level equal to that, even though it's inside of a function, will that chunk of memory remain?
Sure, because if code was something that was passed to you, right, and you do this, code is pointing to some location in memory. That memory location is not going to go away when you return from your function.
And the memory where x17 is stored won't go away either?
That won't go away either.
Because it's just pointing to x17.
Yeah, but this is not really a local variable, right? Now, if you define code within your function, right, and it's just a struct data, and you say code.level equals x17, that's going to go away when you exit. But if code is a pointer to a struct data, and you have it point to some address, and you set that level piece to x17, that will remain in memory. But when you exit your function, this variable code, right, is inaccessible. You may not have a handle to that block of memory. But if you returned it from your function as, say, the function value, then you'd be pointing to this block of memory, and that's still intact. So the scoping gets a little weird with dynamic memory, but in general, things that you allocate with malloc are going to be intact, whether you want them to or not. It's when you don't want them to that you get memory leaks. All right, so code arrow xc equals quote w, right? So single quotes for a character, double quotes for a string. This is not a character. This is an address. Okay, it's an address in memory where you will find a W followed by a null terminator. This is essentially an 8-bit version of the ASCII code for W. Okay, it's a character.
Well, actually, the 3 bucks just replaced that task.
Say again?
The 3 bucks just replaced it.
Yeah, yeah. All right, and then code arrow value equals -100. That was pretty straightforward. And the last part was to set this array named stuff to take on those 10 values in that order. So code stuff, bracket 0 should be 10, bracket 1 should be 9, bracket 2 should be 8, and bracket 9 should be 1. And some people did it with 10 assignment statements, and that works. I didn't take off for that. But you can also do this with a loop. If you don't want to risk a loop on a test, right, that's fine, although in the future I'll probably make it like 1,000 entries. So there's different ways you can loop this, right? So for I equals 0, I less than 10, I plus plus, code stuff. So here's the least comfortable way to do it, right? Find a formula. So for 0, I want 10. For 1, I want 9. For 2, I want 8. So in general, I want 10 minus I. But test it in the middle. Test your edge cases. Make sure this is the right thing. If I is 0, element 0 will be 10. If I is 9, element 9 will be 10 minus 9 is 1. Element 2 will be 8. So that seems fine. But there's other ways you can do this. You can have another variable which starts at 10 and counts down while I is counting up, and assign it like that. One person assigned it to the previous index's value minus 1. That works well. That was kind of cool. So different ways you can do this. All right, so that was question 1. Question 2, you've got this linked list. It's got a sentinel node, which is 99, and then you're asked to do various things. Okay, LL is the address of that first node. Most people nailed this, which was awesome. So this is your sentinel. And I clarified during the test that LL is the address of the node containing 99. That's the sentinel. So this field down here is the struct node that LL is pointing to, the next field of that, right? The field name next in that structure. So LL arrow next refers to whatever this block is down here. It's the address of this next node, which has a 12. And so if we take LL arrow next, and we take the thing that's pointing to, that's this struct node. And so its next field is this block right here. And that points to a 14. And this is LL next, next, next. And that's the address of this last node, which is null. And if you don't like working with next, 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 right, you can name these things sentinel, ABC, or something like that. And set A equal to LL next, B equal to LL next, next, and so on. Okay, so there's different ways you can do this. So the first question asks, what gets printed when you print LL next, next data and LL next data? Well, LL next, next is this block right here. So LL next, next arrow is this node, and the data piece is this 14. So LL next, next data will be a 14. LL next, next data will be a 12. So that'll print out a 14 and a 12. And then part B, you wanted to delete the last node of the list. So you want to get rid of this. And the way we get rid of this from the list is we change this pointer to be null. Well, this is LL next, next, next. So set that equal to null. That chops off that 8 node from the end of the list. But we also need to free this node from memory. And the address of this node is LL next, next, next. Now we can't free it here because after this, LL next, next, next is null. Can we free it before? Without getting into trouble? LL next, next, next is the value of this block. This is some location in memory. This is saying free that location in memory. So that sends us back into the heap. And now we say take this location in memory, LL next, 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 and set it equal to null. And there's no conflict there. The conflict would come if after we free this block, we try to use this piece of data or this next field. Because once we free it, we don't assume that we still have access to those locations. But changing this thing back here to be null after we freed this, there's no problem with that. So you can do it with just 2 statements, or you could save this into a temporary and then set this to null and then free the temporary if you want. That's fine. Yeah.
So, it is fully saying is what I did, but for the second line, can I write out something different instead of null?
Instead of null?
Yeah. Like LL next, 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 next.
Yes, so if you haven't freed, you could have done this, because this is that block right there. And that's how we delete in general, right? We take this and we have it point to whatever this is pointing to. That pulls that 8 out of the list. But that you can't do after you freed, because after you freed, this is no longer available. But you could save this into a temporary, right? Something pointing to it, and then set this, and then say free the temporary. Yeah, that's great. All right, part C. Write some C code to create a new node and point to it with a variable named new. So we want to create a new struct node. So malloc. And the number of bytes we need is just size of struct node. Nobody did struct node star, which was great. I was happy with that because people had trouble with that while they were coding a couple of weeks ago. So we did size of struct node, which is awesome. And then point to it with a variable named new. So we need a struct node star new, which is equal to whatever address malloc gives us back. And then part D, we want to insert this new node between the 12 and the 14. So come back here. We've got this block new. And we want to sandwich it in between the 12 and the 14. So we want to do 2 things. We want to set new to point where the 12 is pointing. And then we want to change the 12 to point to new. So how do we change new to point where the 12 is pointing? New next equals whatever this block is, which is just LL next next. And then we want this block here, which is LL next next, to point to new. So that'll do your insert. So questions on that? All right, so question 3 was queues. So here's the head, here's the tail. And we said insert a 10. So you put a 10 at the tail, and that's sitting inside your queue. We say insert a 20. The 20 goes in the tail behind the head. Insert a 15. That goes into the tail behind the 20, behind the 10. Remove what's at the head, so the 10 comes out of the queue, and now our queue has a 20 and a 15 with 20 at the head. Remove again, the 20 comes out, and our queue looks like this. It just has a 15. Insert a 30, puts a 30 at the tail behind the 15, and then our final remove removes the 15, and now our queue just has a 30. And just about everybody got that right. A few people did a LIFO, so they were inserting this way, and then they were removing in the same order, the opposite order from what they inserted. That's a stack behavior. So double check that. All right, question 4. This was the other linked list question. So you had a linked list where your nodes contained a piece of data, which was a single character, and then a pointer to another node. And your goal was to march down the list and see how many of your nodes contain the character A. Count the number of nodes and return that count. So we want an integer return. Takes an argument, which is a list or a sentinel. So we need some kind of counter inside here, so I'll just call it num. That'll be the number of A's. And when you want to traverse a list, one way to do that is start with the thing the sentinel points to. So you could make a struct node temp, or you could just use send as a temporary, since we're only going through once and we don't care. But let's not get too weird. So let's make another struct node temp and set temp equal to the first data node of our list. So we're skipping over the sentinel, that's important, and we're pointing to the first data node.
So we didn't have to check if that was null.
Sentinel is never null. That's why we have a sentinel.
Sorry, next. We didn't have to check next.
Temp may very well be null at this point. That's okay. Since sentinel's not null, we can always say send arrow next, but temp may be null. So before we use temp, we need to check. But we can do this in a while loop. So while temp is not null. And if temp's not null, then temp is a data node. It's the first data node in our list. And so we could say if temp arrow data equals A, then increment our counter. And then we need to move down the list, so we can do something like temp equals temp arrow next. And go back to the top of the while loop. When we exit the while loop, it's because we got to a node which was null, which means we already looked at the last data node, and then we set temp to what that was pointing to, which was null, and so now we can just return num. And so not a lot of troubles with this. A few things that I saw. So one thing was doing a malloc up here. Temp equals malloc, size of struct node, followed by temp equals send arrow next. Don't do that extra malloc. It uses memory, and unless you free it, you've got a memory leak. And all we need is to say temp is a pointer to a struct node, and then we're giving temp a value. Right? You only use malloc if you want to create a new struct node somewhere. And we don't need a new struct node. We're trying to point to the struct nodes that make up our linked list. So no need for a malloc here, so I took off for that. This business of do we start with sent arrow next or do we start with temp equals sent? There's different ways to do this, and different ways will make sense to different people. So however works for you is fine, and most of the variations I saw on this were correct. But in some cases, you might start off with temp equals sent and say, well, temp is not null. If temp data equals A, well, there you're checking the sentinel's data. That's not good. Or you might say, well, temp is not null. Temp equals temp arrow next. And that could be null, so you've got to check for that, otherwise you risk a seg fault. Or you might say, well, temp arrow next is not null, and see if temp's data is A. But if you do that, as soon as temp arrow next is null, it means temp is the last data node, but you haven't checked the data value yet. So you're probably skipping the last node. So sometimes there is an extra check after the while loop to see if temp arrow data was equal to A, and it would bump up the count once more, and that works fine. So there's different ways to do this. This is not the only way. It's not the only algorithm. Okay, the algorithm, though, is to start with the first data node in some way, shape, or form, see if it's equal to an A, bump up your counter, follow its link to the next data node, and keep going until you've assessed all the data nodes, and then return the count. But different ways to get there. All right, then we had the stack question. So you didn't have to know anything about stacks because I gave you the code here. Okay, but if you understand stacks, it can be easier to sort of grok what the code's doing by thinking about stacky things. But you've got the code here for what push and pop is, and the initial value of SP is 0. So push will do the following. It will store this number n at the location given by SP, and then it will increment SP. Pop will decrement SP and then return what was at that location in the array. So let me just make a page here. Okay, we know SP starts off at 0. We know that these are uninitialized, so we don't know what the value is. So part A says push 10, push 20, and push 15. All right, so what does a push do? Stores the data at the location given by SP, increments SP. So push 10 will store a 10 at index 0, and then increment SP. Push 20 will store 20 at index 1 and increment SP. Push 15 will store at index 2 and increment SP. So in part A, at the end of the 3 pushes, your stack pointer is 3. The values in your memory are 10, 20, 15, and 2 question marks. Right? We don't know what's in 3 and 4. All right, part B says push 7 and then do 2 pops. Okay, when we push 7, we'll store 7 at the index given by SP, which is 3, so this becomes a 7. SP gets incremented to 4. And then pop, remember, decrements the stack pointer and returns the value from the data array. So pop will decrement the stack pointer to 3, and it'll return a 7. And then pop again will decrement the stack pointer to 2, and it'll return index 2's element, which is 15. So at part B, our stack pointer is 2, and the values in our array are 10, 20, 15, 7, and question mark. And we don't do anything in a pop that somehow makes these values unknown, right? Pop is a very simple function. Just return an element from the array after decrementing the stack pointer. So pop changes the stack pointer. It doesn't change any values in the array. So part C says do a pop, push a 7, push an 8, and push a 6. All right, we do a pop that decrements the stack pointer. We push a 7, we store that at the index given by the stack pointer, and we increment the stack pointer. Push an 8, store that at index 2, increment the stack pointer. Push a 6, store that at index 3, and increment the stack pointer. So after part C, your stack pointer is 4, your stack contains 10, 7, 8, 6, and question mark. And then part D, push a 15 and pop 5 times. So push a 15, store 15 at the index given by the stack pointer. That goes right here. Pop, decrement the stack pointer, pop, decrement, pop, decrement. Oh, I did that wrong. Push a 15, store it at that, and increment the stack pointer to 5. And then pop, first one brings it down to 4, second one to 3, third one, fourth one, fifth one. So after your 5 pops, stack pointer is 0, and your stack contains 10, 7, 8, 6, and 15. All right, and then multiple choice. So we talked about this one before, which one's not part of an abstract definition of a queue. So this is based on how the queue is implemented in particular. These other things are calls to interface functions that let us manipulate or interrogate the state of the queue, but C is not part of an abstract queue. Okay, we talked about the segfault one. The problem with B is that Y is looking at the thing pointed to by X, but we don't know what X is pointing to. As soon as you say integer star X, imagine that X is equal to 0. And so Y equals star X is saying, tell me what's at memory location 0. That's a segfault. Okay, C is an easy one. We're just adding 2 integers and storing. D is taking a pointer to an integer and making it point to X. Nothing wrong with that. And A is saying Y is the address of X, print out the value of that address. So B is the outlier there. Part C, write a statement to allocate enough space for an array of 125 elements of type struct big. And I clarified during the test that this has to be something that happens at runtime. So you can't just say struct data big bracket 125. Okay, that's a compile time allocation. So you need to do a malloc. And the easiest way is 125 times size of struct big. So this is how many bytes you need for one struct big. Multiply by 125. That's enough memory for 125 of them. And that's not the same thing as making an array of 125 pointers and mallocing each one to be equal to a pointer to a struct big. That's not giving you a block of memory big enough to hold 125 struct big. It's giving you 125 struct bigs and storing their addresses in an array, but each of those might be somewhere totally different in memory. All right, what utility can help you detect memory leaks? Valgrind. Everybody got that, I think. What would you type to compile a program named main.c if you intend to use GDB to debug it? So gcc-g main.c is the shortest way to do that. That'll give you an a.out, but with debugging symbols, and then you could say gdb a.out. You could also do -o main. You could also put your -g over here. You could also put your -o main back here, and there's other ways that you can do this. In general, these things are independent, but -o main kind of have to go together, right? So a few people did -o main.c. Don't do that, right? That wipes out your source code. But all you really needed here was just a -g and to mention main.c in the compile line. If your directory contains a make file designed to build a single program, what command do you type to build the program using that make file? That's just make. Okay, that's what makefiles do. And then part G, write a C statement that allocates 10 bytes of data, assigns a variable which has already been declared named pointer to point to it, and prints an error message if there's no memory available. So pointer's already been declared, so we can just say pointer equals malloc 10. And then to see if we ran out of memory or not, if pointer equals null, print out an error message. And that'll get you there. So questions on any of that? Yes?
So for the G,
Yeah.
I just did G as G. I mean, did that
G?
yeah.
Okay, what did you do?
I just did as P equal if as P equal 10 and create vendor.
So what is SP, first of all?
Oh, should I define it at first?
Yeah, so how would you define it?
I thought I already defined it first.
So where are your 10 bytes of data coming from? Right, so if we had a stack,
Yeah.
right, and the stack had at least 10 bytes of information in it, then you could try to do something like that. But this was kind of a standalone question, because I don't think any of the parts dealt with stacks. So you need to allocate 10 bytes of memory, right, and that's a malloc statement. All right. Any other questions? That's you, right? Yeah, okay. Well, not much time left, but we're done.
10 minutes, right?
Yay.
5 minutes.
Yeah. Why is this happening? Well, whatever. My computer is like, is anybody else's computer like badly behaving lately? I want to blame like Spectre Meltdown fixes, but it rebooted on me last night while I was doing backups. That was always nice. All right, so ODP 213, right? That was the one due this morning. So that was a basic hash by simply adding ASCII codes and reducing modulo 31. So something like that will work. So it takes in a char star and loop through. String length will tell me how many characters are in the string up to but not including the null terminator. And for each of those characters, we just added to a running sum, and I reduced mod 31 each time, just in case the string was really long, so it wouldn't overflow. And in this case, with this hash function, if you happen to include the null terminator, it doesn't really do any harm because that's got an ASCII code of 0. But usually we go less than the string length, so that excludes the null terminator. And then it just returns the resulting value, mod 31. So that's your basic hash function. So today's ODP modifies that. It's a hash function with a probe. So your function actually takes 2 arguments, the same string as the first argument, but the second argument is an integer, which is a probe number. And the algorithm is to basically do the same hash that you did for the previous ODP. So add up the ASCII codes, reduce mod 31, but at the end add the square of the probe and then reduce mod 31 again. So if the probe is 0, it's exactly the same hash function you had. If probe is equal to 1, then your return value just goes up by 1, right, mod 31. So if it was returning 31, now it'll return 0. If your probe is 2, it'll add 4 to the final sum and reduce mod 31, and so on. So it's like one more line of, not even a full line of code. It's a few extra characters on one line of code. And there's some sample values. So the string hello still hashes to a 4 with a probe of 0, but it hashes 2 different values depending on the probe. And the idea, again, is that if we were using this to go into an array to store our string, right, if there was already something at location 4, we would next try location 5, and then 8, and then 13, and so on. And so we're not just trying successive locations. It's tending to spread out our attempts. And so test bed main214.0, link it up after you think it works, and give it a try. And again, remember that when you input a string using fgets, there's a null terminator tacked on the end. So if you read from fgets, read using fgets and pass that to hash, and you type in hello, enter, you're not going to get these values. You're going to get an extra 10 on there because a new line is a character 10. So it's good to test these things just by calling the hash function directly. Right, so that would hash hello with a probe value of 1. See if it gives you the right result. All right, any questions, ODPs? So tomorrow we'll talk about PA4. It's posted on Canvas now, but we'll talk about the details of it, and I'll show you an example code that implements PA4. I'll show you how it works. And then we'll finish up hashes. And next week we'll start talking about new stuff.